Hello, Vladik. Thanks for joining our podcast today, and look forward to interviewing you.
Hi, Vaughn. Thanks so much for having me here.
We've known each other for, I'm not quite sure, maybe, 7 years, maybe, something like that. We met up at a DDD event, I think.
Yeah, DDD Europe, the first one.
Yeah, okay. And and I've run into you other places, and I think the last time we saw each other was at the very last O'Reilly conference ever, maybe, right? And we didn't know it was going to be the last conference ever because, we were having fun. I thought it was well attended, and then the lockdown, right, about a few weeks later. So anyway, we've been distant but staying in touch, and I contacted you, I think, shortly after I signed the signature series and asked you if you'd like to write a book. And I was amazed, very happy that you decided to.
Yeah, it was after O'Reilly conference at New York City. The next one I attended was DDD Europe in Amsterdam. And actually there I did a presentation about coupling. And right after it, Rebecca Wiersbrock told me, you have to write a book about it. So I jumped on this opportunity.
So, and I just want to mention too that Vladik has a book with O'Reilly that is on DomainDriven Design. I apologize for not having the title in my head right now, but what is the title, Vladik?
Yeah, it's Learning Domain-Driven Design, and it's a book for DDD white belts, for people new to domain-driven design and just making their first steps.
Cool. So it's sort of maybe like my distilled book, a little bit kind of flavor, trying to get people up to speed as quickly as possible. So that's another book people should look at when they want to do that.
Yeah, I didn't want to compete with the with distilled book. It's somewhere in between distilled and the red one. It's a bit longer than distilled, but still shorter than the red one.
Yeah. So you've just finished edits and maybe close to production with the second edition of that book, right? So you added some content.
Yeah, right.
Cool. Well, anything to help people understand this fantastic way of developing software with DDD is quite welcome. So, when we spoke about the book under my series, you came up with this idea of which you had already spoken about on the subject of coupling. And of course, probably, an experienced developer, the first thing they might think of is, of course, loose coupling, but high cohesion, right? And that's just sort of a thing, but do we need a whole book on coupling?
Yeah, that's a great question. And actually, day after I signed the contract for the book, I was chatting with my colleagues at work and told them about it. And one of them, raising his eyebrows and saying, okay, so a whole book just on coupling. So do you need more than one page to say that coupling is bad, but cohesion is good?
Yeah, it's a standard comeback, but actually what I find is that a lot of people, they know that little slogan, but they don't really know how to achieve it.
Yeah. And that's the reason I'm writing this book, to try and change our way of thinking about coupling from this simplistic model of coupling is bad to a bit more elaborate one. One which would allow us to analyze the different dimensions and different types of coupling and how they're affecting software. And instead of fighting it, accept that coupling is a fundamental part of system design. Coupling, the word itself comes from Latin, capulare, if I'm not mistaken, and it means connecting things. So in a sense, coupling is everywhere. You cannot make a system without coupling. So the goal of this book is to introduce the reader to different ways of looking at coupling and evaluating it. And instead of just trying blindly to eliminate coupling as an absolute evil. Instead, balance its forces to design modular software. And actually, not long ago, when this microservices hype started, many companies, and by the way, myself included, made so much mess trying to decompose like a monolithic system into those tiny microservices that are decoupled, and I'm showing air quotes here, and trying to design a system where each microservice can be evolved and implemented independently. But in the end, all those efforts led to distributed monoliths, like way more coupling that the original system had. And that was the motivation for this research. It started by how do we do microservices right? But then I said, hey, coupling is way more interesting than microservices. It's more fundamental aspect of software design. It's more interesting. Yeah, so the goal of this book is to describe coupling in a more holistic way. The different dimensions of coupling, how each one of them affects software design, and how do we differentiate between balanced coupling and unbalanced coupling, and how do we differentiate between essential coupling and accidental one. And of course, the latter one, accidental, is the one that we should eliminate. But the essential coupling is a key to designing modular systems.
Right. And I think fair evidence of accidental coupling, I suppose accidental, or maybe even more so like completely oblivious coupling, right, is the big ball of mud. So you go into one of those older systems and things just reference, and either hold copies or I should say references to other objects, or you name it. What do you say about that? I mean, is that your experience too?
Yeah, of course. And interestingly, big ball of mud, this term, this anti-pattern, was coined way back. And what fascinates me about it is that the same problems that we are struggling with today are not new. They're like ages old. And when I was doing my research for microservices, I read some books even from late 60s, early 70s about system design, how it was done during the days of procedural programming. And basically the same problems we are facing today with, let's say, distributed systems and microservices, etc. It was just defined differently. Instead of services, they had back then procedures. Yeah, so the same big ball of mud were happening back then and they're happening now. And actually, in those early days, there was much more research done about coupling. And today we ended up with coupling is bad, cohesion is good. And again, I want to try and fix that. I want to try and provide a bit more information about coupling. Now, this book, I would love to say that I developed something new or I invented something new, but I didn't. I just read old books and found interesting pieces that apply to our systems today and slightly modified them to adapt them to our current needs. And that's it. So actually, that book is really about relearning what we already forgot.
Yes. And, if I was listening to this or watching a presentation just yesterday by Alan Kay, it was one of his most recent, I guess, keynotes. In case listeners aren't familiar with Alan Kay, he's, basically really a computer scientist. He's responsible for essentially making object-oriented programming, a thing that people know about as that. He's also kind of the inventor of the GUI, the modern GUI. And what really impressed me is that Alan Kay didn't talk about his great inventions and so forth, but he spoke about Margaret Hamilton, who uh, you know, was responsible for writing much of the application software, or all of the application software, for the early Apollo space missions. And I don't remember the gentleman who worked with her. I don't remember his name, but he was sort of responsible for the operating system. So it was two people, and you know, and the forethought that went into this software was just amazing, because they told Margaret Hamilton, don't worry about the astronauts. They will never make a mistake, right? So just write the software to, with the thought in mind that they're going to do everything correctly. And she said to herself, I don't believe that. And so she designed in fail safety and loose coupling, right? Because she knew that if they made a mistake, they could very easily be lost in space, as it were, without some sort of correction. And in fact, it happened on the very first mission that used the software. They flipped a switch when they shouldn't have flipped a switch. And if she had not built in that robustness into the software, who knows what could have gone wrong. And it was really amazing, because she said, yeah, I just didn't trust that was going to happen. But it was actually loose coupling and late binding in some old assembler software, right? I think it was assembly software in a rocket with 64 kilobytes of RAM. So, yeah.
Yeah, that's fascinating.
So tell us more about the research that you did. I mean, there must have been a lot of research that went into this topic. What are some of the things that you learned specifically about it?
Yeah, so primarily I started with the structured design methodology. And it was like a way to design modular software in procedural programming languages. Now, in those early books about structured design, there is quite a comprehensive discussion of coupling, of how the procedures can be coupled to each other. And the terminology defined back then is still being used sometimes, even in our days, in the realm of distributed systems. However, there's a bit, although the problems are the same, the solution is probably the same, but the terminology should be adapted to match our reality. So in this book, Balancing Coupling in Software Design, what I did is I adapted the terminology from structured design a bit to match our current systems, but still leaving the purpose and the way to solve the problem the same as during those early days. Another research that I did was about Khononov, and Khononov was coined in 90s, if I'm not mistaken, as a way to evaluate coupling in object-oriented design. It was coined by Miller Page Jones, and the goal was to use this framework as a way to evaluate coupling in any kind of system, be it procedural, object-oriented, or something that might come up in the future. That the way it was defined in his book. Now, unfortunately, this model cannot be used as it was defined back then in our current reality. So again, I adapted it a bit, its terminology, its terms, and eventually merged it with structured designs coupling as a model for evaluating the amount of knowledge shared between two components of a system. Now, the more knowledge is shared, it acts as a force attracting those components together, as force of gravity, for example. In gravity, it's the size of the object that creates that force, but in our world of software engineering, it's more about the amount of knowledge that is being shared between those two objects. And that's, by the way, one of the dimensions of coupling. I called it integration strength. The higher the knowledge that is shared across the boundaries of components, the higher the integration strength. So another interesting aspect of the research was when I did the, let's call it reverse research. So after I formulated that formula of balanced coupling that balances the different dimensions of coupling, and by that I mean integration strength, distance, and volatility. I did a reverse research to see how that formula applies in the different design patterns, design methodologies that we are using. And I was fascinated to find out that it can be spotted almost everywhere. And the last 3 chapters of the book are actually discussing software design principles like solid principles, methodologies like domain-driven design, for example, and even design patterns like classical design patterns. And there I want to show how that notion of balanced coupling is really implemented in each of those techniques. It's like really at the heart of software design.
Yeah, it's very interesting. So one thing that really caught my attention is this idea of integration strength. Since integration is a big part, I mean, it's almost everything in software today. I've spoken with companies recently where integration is just the biggest problem that they have to solve. So can you give us sort of a concrete example of what integration strength is in a good sense and in a bad sense?
Yeah, sure. Now, if I may, I will switch to our shared ubiquitous language of domain-driven design to give you an example.
Okay.
So let's say we have 2 bounded contexts, and both of them are exposing their operational models. Now, we know that it can be problematic because if that's a core subdomain and it changes often, the model is going to evolve and it's going to affect the boundaries. So we are sharing too much knowledge. But on the other hand, we have the open host pattern, which says that instead of sharing your operational model, define the published language, the model which is intended for integrations, and it compresses the amount of knowledge you are exposing to external components, and it allows you both to evolve your bounded context without necessarily affecting other components. And it also allows you to minimize the amount of knowledge that you are sharing. So in a sense, you are lowering the integration strength between the bounded contexts. Now, this notion can be applied at different levels. It can be applied even between methods in a single class, because let's say we have 2 methods and both of them are relying on the class's members, like private variables. Now, that means that both methods have quite some knowledge about the context they are working in. On the other hand, we can go a bit more, let's say, functional way, and instead of using that shared state, pass the information each method needs as an argument. So again, we're compressing the amount of knowledge shared between those 2 entities. In this case, it's 2 methods in a class, but we can apply the same reasoning to classes, modules, services, or even systems.
Good examples. Thank you. So you have some examples in the book of actual software designs, and can you tell us about those?
Yeah, sure. So of course, I wanted to add as many examples as possible. Now, most of them are based on my experience. In other words, mistakes I did in the past. The creative ways I found to experience coupling and how it can cripple your software. Now, what I hope to do as the next project, after we finish with the book is to do an online training for Pearson, where we're going to go through implementation of a game, like a mobile game, and distributed system, and something which sounds totally unrelated, like a bash script. And there I want to show how the same concepts apply as those different, seemingly unrelated types of software.
And it may seem to people, who cares if two batch scripts or one batch script is coupled to something, and maybe actually it isn't that important, but maybe it is. And especially in the days of DevOps, right? So we're writing a lot of scripts to take care of build and pipeline types of things. So like why choose scripting as one of the examples?
Yeah, because as you said, during our, let's call it DevOps era, I see so many teams having those incomprehensible YAML scripts, which are like write only. They cannot be read, they cannot be modified. But hey, their purpose, they're existing there for the purpose of being able to evolve them, to change them in the future, but they are just not designed correctly. And at the core of those design issues is missing balance of coupling forces.
Wait, are you trying to say that YAML can be confusing? No, good example. So, well, so if you could elaborate on what you think the game has to show about coupling and loose coupling or tight coupling.
Yeah, so a game is going to be based on some open source example that can be found on GitHub. Something classic like Snake, and it actually makes it really simple to demonstrate those issues of misaligned coupling in the source code. And of course, what I want to show that the goal of balancing coupling in the case of the game is not for the purpose of aesthetics, like to make the code more beautiful. No, the purpose is going to be to see how it will make it easier to evolve the game, to change its rules, to change its requirements, etc. So again, evolution is the key here. And that, by the way, brings us back to dimensions of coupling. So in the book, we're discussing 3 dimensions: integration strength, distance, and volatility. And the last one, volatility, is really important. It's like the dimension of time. How often the coupled components are changing? Because, if you have a system which is insanely coupled, but it never changes, it's like a tree that falls, but no one there to hear it fall. So it doesn't make a sound. So in that case, well, we can allow it to be coupled if it's not going to change. But the point is to demonstrate that, hey, we are building software which is supposed to be soft. We expect it to be easy to change and to evolve. And that's why we need to treat coupling with all the attention and care it deserves.
Nice way to express that. I was thinking another relationship with coupling, loose coupling, and so forth, and with domain-driven design is when a bounded context depends on the events from another context. Do you have any pointers on how to deal with the coupling of the events and to, like let's say we have an upstream context and it publishes some events and a downstream receives those. How do we not just give them information, but also protect that customer from, the effects of ongoing changes to the events? I don't know. Do you have any pointers on that?
Yeah, of course. That's a terrific point and that's a part of the simplistic model of coupling. Like usually people say, hey, you have to communicate asynchronously because that's going to be a loose coupling, which is not really the case. Like I can give you a ton of examples, like two components communicating synchronously, two components communicating asynchronously, and two components not communicating at all, like really not communicating with each other. But in those three cases, the highest coupling will be in the last two cases, where they're communicating asynchronously or not communicating at all. So when they're communicating asynchronously, well, they may be sharing, again, their operational model, how their business logic is implemented. So any change to that, to schema of those events is going to ripple through the boundaries and affect the components that you're integrating with. And it's especially true for event source systems. Like in one of the previous companies where I used to work, we had this aggregate that had around 75 types of events that were used inside the aggregate to implement event sourcing. And we said, hey, we have those events and asynchronous communication is flexible and evolvable. Let's just expose them outside across the boundary. And we found ourselves in such a huge trouble when we had to evolve that event sourced model to change those events because they became the integration contract. And that's what happens quite often when people are using asynchronous communication without considering the integration strength, the amount of knowledge they're sharing, either about the function of a service, like what it's supposed to do, or its implementation, like how it implements its function, its implementation details. And it can be easy to do it using asynchronous communication. And again, that's just another way to share too much knowledge. Now, the second example, which is crazy one. So let's say we have two components in a system not integrated with each other at all. No error, no REST API, no messages, nothing. But they're insanely coupled. How can that happen? That can happen if, for example, both of them are implementing the same business function, the same business rule. And when the rule changes, it has to be changed simultaneously in both of them because otherwise it will corrupt the data. Now, one may say that, hey, that's a theoretical example, it can happen, and it happens all the time. For example, when you have operational system and a data analytics system, and both of them implementing the same business rules. I saw it happening quite often. So in a sense, those components are not explicitly connected to each other, but they're still coupled by exposing a lot of business knowledge.
Yeah, I think one thing that people miss about don't repeat yourself is it's not about the data, it's about knowledge. You don't want to repeat knowledge. And when you leak knowledge into multiple places, then you've got this big problem of, the worst being not even that you have to change the code, but that you don't know that you should change the code, right?
Yeah,
and then
exactly.
these bugs creep in and because teams aren't communicating, is there ever a problem with human communication in software? Absolutely, all the time. So yeah, try to avoid those situations at all, about all cost. Yeah.
Mm-hmm. Yeah. About communication, when I was in university, I did a research about why software projects fail. Like there are different studies around this subject, why so many projects are not delivered on time, on budget, or on value. And like a vast majority of findings are all about communication. It always has to do with communication, either by communicating requirements or communicating the progress, etc. The common denominator is always communication.
Very true. So once again, Mel Conway, isn't it unbelievable? I mean, about the same time that this Apollo mission occurred, and we had this genius woman, looking after the astronauts, even when everybody thought they would never make a mistake. Around that same time, I mean, it was probably just within months or years of that, a few years, here's Mel Conway teaching everybody a lesson about communication and how it reflects into software, and it's unavoidable.
Mhm.
And if you and I think what people don't get so many times is that they just hear this, well, the communication structure will have a direct impact on your software design or your system design. And so they say something so simple like, well, that means if your organization has 3 teams working on the system, then you'll have 3 subsystems. And actually, for domain-driven design, in the first place, that tends to be untrue, because very readily one team can have multiple subdomains, a la the bounded context reflecting them, and it's also overly simplified, right? It's just that what we're talking about at this level is that people don't communicate to the the detriment of the system quality itself. And this is what I think Mel Conway doesn't get enough credit for. And, when there are techniques described like the reverse Conway maneuver, it to me, I mean, that's cool. Someone gave this a name, but at the end of his paper, Mel Conway discussed that directly. To me, there is no reverse Conway maneuver. He told you in 1967 what to do about it. So, okay, you want to give it a name and maybe sound like, you've invented something. I don't know. But man, if you really read his paper and let it sink in, it's way deeper than people give it credit for, even today, even though there's so much attention given to it. No, reread that and really think about the problems that we still have in software, and it is amazing. So, like you said, go back to structural programming, procedural programming, right? And we learned so much from that, what people would consider old and no good anymore.
Yeah, yeah, definitely.
So, Vladik, do you have some kind of parting advice for people who are facing this problem, that maybe insidious problem, maybe they don't even know that they have? What can they look at in their code or across microservices to give them this sort of instantaneous aha moment? We got to change this. This is, a bad coupling.
Yeah, sure. So I would start by evaluating the amount of knowledge shared between the two components. Second, evaluating the distance between those components. Now, the distance can be short. For example, the shortest one is 2 lines in the same method, or longest one when we're talking about components located in different systems or different microservices. And third, how often the components are expected to change. Now, give some numeric value for each of those dimensions. Let's say from 1 to 10, how much knowledge is shared, 1 to 10, how distant the components are from each other, and 1 to 10, how often they're expected to change. Multiply those values, and if you're getting a high number, then probably you have a problem. Now, on the other hand, if one of those dimensions is 0, no matter what the other two are, because the end result is going to be 0. So that multiplication of knowledge shared, distance, and volatility gives you the maintenance pain. So make sure that your maintenance pain is 0. That would be my first advice. And my second advice would be to read the book, because there you will find a more elaborate formula that expresses not only the maintenance pain, but also the complexity of the system.
Right. And this is obviously one way to communicate, at least the beginning. So we are communicating to other architects, other engineers, how to, look at coupling and how to deal with it. But in the book and in your upcoming training on, the O'Reilly Live lessons through Pearson, Addison, Wesley, they're going to have so much more content and kinds of content flowing toward them that it will just make this much more clear to them. So we're doing everything we can to communicate. to everyone how to take care of this problem. So it sounds to me like no matter what software we are involved in writing, we better consider every piece of software we're looking at, the coupling distance, the various attributes or properties of coupling that you've been discussing, and look into it and apply it to whatever you're doing, but don't underestimate the impact that poor coupling can have on any piece of software. What is that fair?
Yeah, sure. Now, when we are talking about software, we usually mean software systems. Like any software is a system, whether it's object oriented, it's a system where the classes are the components. If it's a distributed system, then the services are the components. Whatever software we are implementing, it's always a system. And a system is components integrating with each other. And as Ruth Malan famously said, system design is all about boundaries, what's in, what's out, and what goes across the boundaries. Now, what goes across the boundaries is coupling. And that makes coupling an essential part of system design, no matter what system you are designing.
That's really good advice because it reminds me of this IMAX film that I saw years ago, and I don't remember the name of it, but it was like focusing on powers of 10, right? So you could look at some little tiny, atom and then zoom out a power of 10 and see a different level of detail. And then if you keep zooming out powers of 10, pretty soon you're at like this sort of, as far as we know, where the universe extends, and no doubt further, but we just have no idea what's out there. But the point is, these powers of 10, if you apply them to software, it's very similar, right? So two variables that are modified in a single method right next to each other can be representative of the kind of coupling that two subsystems in an entire large system, and let's say that they are microservices or even lambdas, right? Like function as a service kind of thing. And so you can really gain from this at every level. Is that fair?
Yeah, of course. Yeah, definitely. And especially that example of lambdas and that poor naming, in my opinion, function as a service, because people often take it quite literally and implementing a method as a service. And what you're getting is a lot of knowledge shared across big distances, because those are different components. Each lambda is a component. And when they have to change, often you'll get a lot of maintenance pain. And actually, your example of an atom multiplied by 10, it's pretty close to the topic discussed in one of the later chapters of the book called Fractal Geometry of Software Design. And in that chapter, I wanted to show that we have this way to evaluate coupling, and we can use it at different levels. It's ubiquitous, whether you're looking at a method, a class, a module, system, or a collection of systems. The same rules of coupling apply everywhere.
Well, I'm glad we agree, and I have not read that chapter, so it is interesting the way that we look at things. But it did, when you said that previously, and the whole discussion kind of has reminded me of those scoping kinds of ways of looking at things. So it's very powerful. I can't wait until people have the opportunity to read your book. I think from what I can tell, maybe you'll have a published book, in maybe March of 2022, something like that.
Yeah, that's the goal, March of next year. And
Yeah.
probably there are going to be an early release earlier for brave souls that want to read unedited draft.
Yeah. Well, yes, O'Reilly and Pearson have, some sort of partnership there. So we are able to get our books on the O'Reilly learning system and as rough cuts. Now, it depends. Our book was released on rough cuts after it had already gone through copy edits and so forth. Originally, my iDDD book was rough, when they released it. So maybe they'll get your book in that form, or maybe a bit later when it's quite clean. Who knows?
I know that Learning Domain-Driven Design was available as an early release, but I wanted to change the name to Embarrassing Release.
Yeah. Well, yeah. Authors, we have this sort of, we want people to read, we want to be able to help people. And then we've always got this sort of like, I hope I did that correctly. I'm with you there. Well, Vladik, thank you so much. I think we've given this a real fair opportunity for people to learn about, coupling, and at least an introductory form. So I look forward to when we can see each other again and sip some cognac. Maybe I think you could use a really nice bottle of cognac right now with everything that's going on and the pressure of there, he's got it. I know. So yeah, I can't wait till we can get together again. It would be very nice to see you again, and face to face, and hopefully that will be sooner than later.
Yeah, I can't wait as well. And I want to thank you for inviting me to write this book. And it's a huge honor for me to be on this signature series.
And it's likewise a huge honor to have you as an author in the series, and for your friendship. Thank you.
Thank you, Van.